early. All right. So module 2, analytical methods and separation techniques. All right. So state the meaning of the following terms: electromagnetic radiation. What's that? Don't play with my answers, no. These are simple definitions. What is your response? Okay, sure, that is a characteristic of electromagnetic radiation, but is it the definition of electromagnetic radiation? Because you gave me a characteristic, of course, of course. So, any definitions in the chat so far? Let me check. No? Alright. So, I would describe an electromagnetic, or, well, not an, but I would describe electromagnetic radiation as as an energy wave, right? Or a disturbance. Energy wave, or what we would call a electric and magnetic disturbance, right? Let me take that capital D down, right? Traveling, I can traveling through vacuums or hold on. I wouldn't put traveling. Okay, that can hold on. Let me just fix up everything as it relates to the words. But this would be generally it. Alright? That would be my definition here. And we're looking for a one marker. Alright, just a one mark response. So I would actually remove the energy wave because that's assuming so too much. So it's really and truly just a disturbance, it's a wave, right? Containing both a magnetic and an electric component, right? Traveling with the same wave front, etc. etc. Ah, you guys do physics. You guys can do that, right? Lovely. What is wavelength? Okay. So the distance between I wouldn't okay. Hmm. I think the physics in me is trying to stop you from using that definition. 'Cause if you use that definition, you're technically only assuming that it is a transverse wave. Because what about the compression and the rarefaction of our longitudinal wave? But we're gonna continue. So distance between successive crests and troughs. Right? So just looking at something like that. So successive crests and troughs. Um I guess so. That's more or less what it is. Right? So we have a wave. I'm looking at the distance between these two, and we'll call that lambda. What is the frequency of the wave? Oscillation, full oscillation. So the time taken to complete one full oscillation. Are we very sure that that is what we want to say? Is that true? The time it takes to complete one oscillation is what? A period. That's what a period is. Alright? Time to complete one oscillation is a period. The frequency is 1 over the period. Yes. So while the period is how long it takes to complete one oscillation, right? The frequency is the amount of oscillations per second. Ah boy. Um English. Lovely. So write the formula which relates speed of light to wavelength and frequency. That's supposed to even take 30 milliseconds to answer this. What's the answer? No, sir, we're taking way too long to answer this question. Go ahead. Beer-Lambert's law are going to fight you. I going to fight you. So C is equal to lambda nu, or lambda is equal to C over V, not true? Or, you know, those different equations, many iterations of it. Beer-Lambert's law is absorbance is equal to the permittivity times the concentration of the solution times the path length. That's Beer-Lambert's law. That is not what we're asking for here, you know? So I know you're ready for the module 2 questions. Let's shout out Beer-Lambert's law. Let's see. Alright, so let's go. So using the formula there, we must calculate these things. That's literally it. Right? So looking at the corresponding um electromagnetic radiation, we must use the speed of light as 3 times 10 to the 8th meters per second. So let's look at this. So we have the wavelength as that. What would be the frequency? We can calculate, no? Because if the frequency, so I have lambda speed of light and the frequency. So what would that be? How would you calculate it? What's the answer? Rather. What's the answer? Can we transpose to get the frequency here? What would the frequency equal? Frequency nu is equal to what? Lovely. And if we have that now, what is the response? The response here is going to be 3 point something. What's the response? So 3 times ds to negative 13. Lovely. And this is infrared, not true? Alright. And how would you get the wavelength here? How we have to do is transpose to get the wavelength, which I think is going to be. Wait, if you divide it by 3, what's your speed of light is 3. So if you divide by 3, you're gonna get 3.16 times 10 to the 0 power, alright? Or something like that, or 10 to the first power, maybe. We're gonna end up with something like that, and if it is a 0 power, it's going to be radio waves. Alright? So we're done with all of that. Is Christine in the meeting? Auntie Christine is in the meeting, and part C is definitely Auntie Christine's question, because she know all the transitions. Right? So when a covalent molecule absorbs UV visible radiation, electrons are promoted. This phenomenon is known, well, it's the basis for UV vis spectroscopy. Complete figure 2 by inserting arrows to show all possible electron transitions in the molecular orbitals indicated. So that's the first one. We're going from the bottom going to the top. First, what's the first viable transition for UV? Okay, so pi to pi star, n to pi star. What else? N to sigma star and sigma to sigma star. Not true. Well, sigma to sigma star is not possible. Okay, sigma to sigma star is possible for UV, but wait, hold on, hold on. For UV visit is pi to pi star and n to pi star, right? N to sigma star, that is for UV, not true? Are we sure that sigma to sigma star cannot work? Hmm. Mm-hmm. Mm-hmm. Interesting. Yes, it is. To be very, very sure, let's make this very, very clear. There are technically four main electronic transitions, right? But three of them are most common in the UV vis region. Go ahead. Okay. Alright. I mean, the thing is, no. Where Mark. Go ahead. Alright. They're not necessarily related, so no. They're possible. They're possible, but Cabe asked us to look at the three that are most related to UV. Alright. So we're gonna be working with that. List the transitions from C to C1 which would normally produce absorption. Okay, so that question implies that we need to write all of them. Right, so let me just. So that question implies that we need to write all of them. So that is also one, right? So based on that question, yeah, it implies that we need to write all of them. So we're going to write all of them, all transitions, and now we're going to list the transitions that are only viable within our UV region. And those transitions are what? All right, working with stuff like that. So the thing is, no, remember to always read through the questions and stuff like that because the question up there, we could leave the three, but based on what this question underneath it says, I'd put all of them. All right. So let's look at this now. The absorption of an iron thiocyanate solution containing 0.005 rather moles of iron per milliliter was reported as 0.4900 at 540 nanometers. Using Beer-Lambert's law, A is equal to epsilon CL, calculate the specific absorptivity including units of iron thiocyanate, assuming that 1 centimeter cuvette is used. Why? How you come up to that conclusion? Okay, okay, okay. So we're saying that the equation given is A is equal to epsilon Cl, right? And we're asked to find what? What are we finding? The absorptivity, right? That means that epsilon is equal to A over Cl. My bad, why did I write the A like that? Alright? So this simply means now it is going to be 0.4900 over 5 times 1, which should give us now, if it is divided by 5, that's going to be 0. What's the answer? 0.0 something. What's our answer, guys? Hello? 98? Is that the response? The, and then it's liters per mole per centimeter. Per mole per centimeter. Liters per mole per centimeter. Alright? You hope they bring it? Here's the stuff. 4 easy marks. Alright? Lovely now, IR spectra. The IR spectra in figure 3, 4, and 5. I'm so sorry. This is so lovely. Belong to the compounds 3-methylbutanol, heptanone, and methylpentanone. Right? Identify each of the compounds from the IR spectra provided, figure 3, 4, and 5. Justify your choice by indicating the bands on the spectra used to verify the identity of the compounds and indicate the functional groups responsible for the bands in each case. Look at that now. What is this? This is where you're going to look at your data sheet now. Alright? So you're going to take out your data sheet and you're going to realize that there's supposed to be a broad peak at 330 per centimeter for a hydroxyl stretch. Right? So we're going to realize here that the answer for this is going to be our alcohol. Alright? An alcohol specifically. Alright? So this is going to be our 3-methylbutanol, not true? So this would be the OH stretch. OH, that is a justification. Go ahead. Okay. Mm-hmm. Okay, let's see if the other peaks are broader. This is the OH then. This peak is broader than the other one, right? This is the OH peak. So this is the OH. Alright. So the other one, you think that this up here is CH? Mean a carbon and a hydrogen provides a peak at around 3000? Are we sure that's the case? This is what you need the data sheet for now. I'm working off of residual memory of the data sheet. So if you have a data sheet, you can pull it up and we can go through this. This one feels... No, 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 no. What is this one? This one has a peak at around 1700. This is a carbonyl stretch, right? It's a thin carbonyl stretch. So this would be what? A carbonyl group here. So this would be C double bond O. So you guys need to look at the group. So if that is a carbonyl stretch and that is OH, then that means that this one would be a ketone. Well, ketone based off of this group here. Alright, so the OH peak. So let's start let's start the method of elimination, right? We identify that figure 2 is the OH, right? All in agreement? Alright. So this is a 3-methyl butanol. Alright? Lovely. We must look at the data sheet, right, that we must be given, right, to define whether or not this is carbonyl. Go ahead. How do we know that it is 3? Oh, it's in the question. It's in the question. So we're given 3 compounds and we must match them to the thing. So because that's the only alcohol, we'll put that there. Right? This should match a carbonyl group. Who has the data sheet? This should match a carbonyl group. Right? This one should be the is it the key, is there a ketone up here? There's a, okay, so there's a ester and there's a ketone. So we need to know which one represents the ester or which one represents the ketone. Do you guys have the data sheet? You can send it in the WhatsApp group, please. No, I can't continue using residual information from what I saw on the data sheet 2 years ago. The photographic memory kind of gone. Where's the data sheet? So we can have a look at it. Any? Alright, so I'm just going to use an IR spec table if we don't get that data sheet in time. Alright. So for amines, well, we're not going to be using amines here. A picture? Alright, so let me have a look. So in the group. Okay, lovely. Thank you, thank you, thank you. Alright, so free hydroxide. No, we don't have any free hydroxide like that. Alright, lovely. So we're looking at this one. This one has a stretch right before 3000. Right, so that would be around 2800 thereabouts. Mm. So saying that is CH. So this with these questions, you really just have to look at the datasheet information and like match what you need to match to them, right? At around 1300, we have this peak here, this peak that we have here, which is reminiscent of the carbon to oxygen single bond in esters. So I would put the ester here. So this would be the methyl pentanoate, and from that, the last one would be pentanone. All right. So this would be the ester. This would be the methyl pentanone. All right. And then the last one would be the heptanone. Heptanone should have a stretch around 1,700 thereabout. Yes, it does. All right. So this is the heptanone. Right. And then the justifications would be you stating where the stretches are, and based off of the data sheet, this is so, this stretch is seen here with that wave number, etc. Right? So that's what you need to do for your justification. Everybody's okay with this? Everybody okay? No? Alright, so what we're saying, when we have the data sheet, Somebody sent it in the WhatsApp group so you can look at it, right? For the data sheet, what you're gonna be doing is comparing the numbers down here, the wave numbers down here, to what is on the data sheet, right? So if the data sheet says you need to have a strong peak and etc., right, at specific numbers, you're going to be matching those on the diagram. All right, we're going to be matching them on the diagram, right? So based off of, is this the first one? This should be methylpentanone. My apologies, methylpentanoate. All right, but what we're looking at that, right? So the thing is now on the sheet that someone sent in the WhatsApp group, we're saying that there are expected peaks here, right? So there's a alkyl group. So there's a presence of a lot of alkyl groups, which comes from the methyl pentanoate, right? There's a lot of alkyl groups there and you see that stretch around near to the 3000 range, right? And we're saying now that there should be a stretch, right, at around 2000, well, not 2000, 1700, somewhere around there, right? So we're going to be looking at the data sheet and matching it to the stretches on the graph, right, to see which functional groups are present. And from the functional groups that you identify in the graph, you're going to choose your compound. All right. So this stretch here is significant of the C single bond O in esters. That is what this stretch here signifies. Right? So because it's signifying that in an ester, the only ester here is methyl pentanoate. Right? The next one, we should know that there's a large or a wide stretch, right? For the hydroxyl group. This is something that would study, right? So this would be reminiscent of the hydroxyl group there. Right? So that would be the alcohol. And then here now we're gonna have a strong stretch, right, around 1700 here. That is significant of the double carbon double bond O, or the carbonyl group within aldehydes or ketones or carboxylic acids. And because we don't have any aldehydes or carboxylic acid, this one must be the ketone, which is heptanone, right? So we just need to know how to identify them based off of the wave number given to us. All right. So I am going to say this even though it won't be helpful at this point in time. IR requires practice. IR requires practice. If IR is to come, you'd have had to practice IR to get the answers. E. A student is asked to prepare a solid sample for analysis using IR spectroscopy. Describe 4 steps to be taken by the student in preparing the sample for analysis. There are 2 ways. There's a dry and there's a wet. Alright, so give me a method to prepare a sample for IR. Almost at module 3, almost done with our review. What's the first thing we do? Grind the sample, not true? We'll grind the sample into a fine powder, right? Then we mix it with inert salt, which is most likely going to be potassium bromide, right? To form a pellet. Then we compress. Yes, you can. Sodium bromide can work as well. All right, form a disc, and then we can insert into the IR spec machine, spectrometer. right? The IR spectrometer for analysis, right? It's really simple. You just need to describe the grinding, the mixing with the inert salt, right, and the creation of your pellet and your high pressure disc, and then you can just put it in, right? Give one reason why the plates used for IR spectroscopy are made with sodium chloride. Lovely. Ionic compounds. Go ahead. Okay, no problem. All right, no problem, Christine. All the best. No problem. So IR compounds are not IR. Well, sorry, ionic compounds are not IR active, right? So it won't interact with the beam. It won't cause any interference, and that is the end of module 2.